class. In today's video, we're going to be talking about section 7.5, real numbers. Now, if you remember last time, we talked about the rational numbers, or at least in the last chapter, or earlier this chapter. I'll get there eventually. We use this cue to represent our rational numbers. Those were our terminating decimals and our repeating decimals. There are, however, decimals, we know, that don't terminate or repeat. Definition. A real number, which we denote with this R, kind of looks like the paragraph symbol, but an R, is any number that can be written as a decimal. So that means they can be non-terminating and they can be non-repeating. So some examples of non-terminating, non-repeating decimals are pi, which we approximate as 3.14159, and so on and so on. But the number itself never terminates or repeats. Another number which never terminates or repeats is the number e, which is approximately 2.718, blah, blah, blah. It keeps going and going. And so you're like, okay, well, these are really special numbers. This one here is our ratio, because if we have circumference is 2 pi r, pi is r, and if circumference is twice the diameter, pi is the special 2 diameter over 2 radius. It's that ratio of diameter to radius. And we won't talk about where e comes from. But you're like, well, that's a special ratio. Where else might we see these? Well, we see these a lot in square roots. Square roots. Or cube roots and other roots. So, definition. A square root of a non-negative, and that's important, a non-negative number, a, is a number x such that x squared equals a. And so let's look at this grid, which is 9. Well, if I break this down to 3 and 3, we have 3 squared equals 9. So we would say that the square root, which we use this symbol of 9, is 3. And so we say the square root of 9 is 3 because 3 squared equals 9. And here we said non-negative, right? That the non-negative number, x, such that x squared equals a, is the square root. But 3 isn't the only x such that x squared equals 9. Negative 3 squared is 9. So this gives us a definition. The principal square root, so principal square root is the non-negative number x such that x squared equals a. So in both cases, a is non-negative. Because if we would try the square root of negative 9, there is no number such that x squared is negative 9. Because we would somehow need to get like something times a something to give us a negative. And if we have 3 times 3, we get positive 9. Negative 3 times negative 3 is also positive 9. And later, this gives us rise to complex numbers. And we won't talk about those today, but I want you to know that we have the complex numbers, which is the c, and that's where we have the square root of negative 1, which we abbreviate with an I, which are also called imaginary. But again, this isn't the focus of today. Our focus is on our roots. Because if I take the square root of 5, well, there isn't some nice neat number that gives me it. And if we put it into our calculator and we take the square root of 5, well, it's going to approximate that. The square root of 5 is approximately 2.236. But it turns out that never terminates or repeats. And the same is actually true of any non-perfect square. The square root of 2, the square root of 3, the square root of not 4, because that's 2, square root of 5, square root of 6, 7, 8, 9, and that one's a 3. But all of these numbers, so the square root of any non-perfect square is irrational. Now I'm going to walk us through why that's the case. But I'm never going to ask you to prove this. I will walk through the proof, and just being able to nod along with it is enough. So my claim, the square root of 2 is irrational. So to prove this, suppose the opposite. Suppose the square root of 2 is rational. So rational numbers can be written as fractions, i.e. m over n, with m and n both being natural numbers. So, in other words, we're supposing the square root of 2 can be written as m over n. And now, whenever we have a fraction, we can write it in lowest terms. So suppose m over n is in lowest terms. Now, square root of 2 times n is my m. And so what that means is I can square both sides. So 2n squared equals m squared. And now we're going to have to go back to our meaning of divisibility. Well, if m squared is 2 times something, we know 2 divides m squared. And if 2 divides m squared, 2 divides m. If 2 divides m can be written as 2 times k for some natural number k. But if we substitute that, 2n squared equals 2k squared. Well, that means 2n squared equals 4k squared. And if I divide both sides by 2, n squared equals 2k squared. But what do we say that means? Well, that means that 2 divides n squared, and 2 divides n. And now I say that means we have a problem. We said that 2 divides m and 2 divides n. Now that means our fraction has a 2 in the numerator and the denominator. So m over n has a 2 in the numerator and a 2 in the denominator. And actually, let's go ahead and write this. So if 2 divides n equals 2 times j for some j in my natural numbers. Specifically, m over n equals 2k over 2j, which reduces. And it specifically reduces to k over j. But what did we say? We said suppose it's in lowest terms. But this said it isn't in lowest terms. So m over n can't both be in lowest terms and reducible. This is a contradiction. This is a contradiction. So since assuming it was rational led us to both it being in lowest terms and not in lowest terms, this is a contradiction. So our supposition that the square root of 2 is rational is wrong, and the square root of 2 must be irrational. So to talk through that again, I wanted to show that the square root of 2 was irrational. Well, I said, well, suppose the opposite's true, that it's rational. And since it's rational, it can be written as a fraction, namely some m over n, where m and n are natural numbers, and n isn't 0, right? So we'll add that restriction. N can't be 0. So suppose that that square root of 2 is that rational number, m by n, and it's in lowest terms. Well, the square root of 2 times n equals m from this equation here multiplies both sides by m, so we can square both sides, and we get that 2 divides m squared, and 2 divides m. Now from our definition of divisibility, 2 dividing m means that m can be written as 2 times some natural number k. And if we substitute that back into this equation here, 2n squared equals m squared, we get 2n squared equals 4k squared. Now if we divide both sides by 2, we get n squared equals 2k squared. But so since n squared can be written as 2 times a number, we get 2 divides n squared, and if it divides both, it has to divide one of them. So we get 2 divides n. And so 2 divides n means that n is 2 times some other number, natural number, j. But what happens when we do that is that m and n both have a 2 in the numerator and a 2 in the denominator, because specifically m over n is 2k over 2j. But that reduces, specifically reduces to k over j. But that's a contradiction. So our supposition that the square root of 2 is rational on our very first line is wrong, and our square root of 2 must be irrational. And now you could repeat that proof for the square root of 3, the square root of 5, the square root of 6, the square root of 7, and so on and so on. So it's important, right, to just know that all of our square roots of non-perfect squares are irrational. And we get the same, or at least a similar finding for cube roots and so on. But let me first give us an outline. Real numbers. Well, our real numbers are all of our rational numbers. Right, those were our x. So the x is some a over b, a b natural, b not equal to 0, our terminating, repeating decimals. Right, that's our rationals. And we also had our integers. That was our set, -3, -2, -1, 0, 1, 2, and so on, which contained our whole numbers, which we can write like that. So our 0, 1, 2, and so on. And our natural numbers, 1, 2, 3, and so on. But our real numbers is all of these and our irrationals. And so we'll use this double I for our irrational numbers. And I contains, but isn't equal to, because it has more things. For example, all of our square root of x, x not a perfect square. But it also has pi and e, the cubed root of 7, and so on. So let me define cube root. Other roots. The cube root of, say, 27 is x, such that x cubed is 27. Well, we can draw a picture. Right, so we have 3 here, and we can picture 3 such slices, so that this gives us 27 cubes. And 3 times 3 times 3 is 27. But notice the cube root of -27 is -3, because -3 times -3 times -3 is negative, 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 negative 27. So to generalize, generally, square or even roots are defined for positive numbers. cube or any odd roots are defined for positive and negative numbers. And whenever we have the cubed root of, say, 7, that's going to be irrational. I won't prove why that's true. You can take my word for it, or you can emulate our proof for the square root. And more generally, whenever we have a rational exponent, x to the 1 over n is by definition the nth root of x, as long as the nth root of x is meaningful. So for example, negative 2 to the 1/2 is the square root of negative 2 is not meaningful. Right, because we can't take the square root of negative 2. And x to the m over n is by definition the nth root of x to the m whenever the nth root of x to the m is meaningful. So if we have negative 2 to the, let's see, 2/4, that is negative 2 squared to the 4th. So we have the 4th root of 4, which if we put into our calculator, we can find out, but I'm less interested. The 4th root of 4 is about 1.414, because if we multiply that by itself, we get 4. If we multiply it by itself 4 times, we get 4. So our takeaway is, even after we included all of our fractions, there are fractions that neither terminate nor repeat. And those non-terminating, non-repeating decimals make up the rest of the real numbers. They most commonly occur when we take the square root of any number that's not a perfect square, or the cube root of any number that's not a perfect cubed, and so on and so on. And so from that, we can generalize and talk about our even roots are defined for our positive numbers and our cube roots being defined for negative numbers. And our rational exponents, x to the 1 over n is that nth root of x, and x to the m over n is our nth root of x to the m, whenever it's meaningful. And so while 2/4 does reduce to 1/2, negative 2 to the 1/2 isn't meaningful, but negative 2 to the 2/4, because we evaluate our exponent and then our root, we get the 4th root of 4, and we get 1.414, and so on and so on and so on. And that concludes our discussion of real numbers.